Okay, seems like it's going. Can you guys hear me? Okay, good. Having fun at Monsanto? All right, we'll see how this works. Okay, did you guys have any questions from last time? Did you guys get a chance to look at the notes? Did you guys get the mountain of resources I sent to you in terms of books and papers?
Yeah, I got it, yeah.
It's actually a published book now. You can buy a hard copy of it. And I'm sure with the hard copy comes probably some software, some scripts and data and stuff like that, I'm assuming. Maybe a CD. I'm not sure, I haven't purchased it yet myself. But until, I downloaded that I think in December or January. And until that point it was available online, but I don't think since it's published now it's available online. So I'm not sure what's changed between those PDFs that you got and the copy of the book, if they've edited anything or not. So that's there, and you know, I don't expect you guys to read that entire thing. It's there more of as a resource, sort of back up what you're learning, and as a reference for looking things up. So last time we were talking about linear models. Did you send me these notes, Mark? I don't think I sent you these, did I?
I can know that. I don't have those slides.
Yeah, these slides I just made for today. I made these slides today because normally I may use the whiteboard, but since we're recording this lecture, I need to have everything on the screen, so I'm going to be using slides. All right, so last time we talked about basically leveraging the covariance matrix among our residuals in our linear model to adjust for spatial effects in our field. And last time we talked about perhaps possible field layout, where we have a field layout here. This is an example here that consists of 12 plots, and it's laid out in this row column design, which is a common feature of all of our field designs, just naturally. So if you have a spatial trend in this field, going from top to bottom and left to right, you'd expect that experimental units in one part of the field are going to resemble each other more than experimental units that are in distant parts of the field. Okay, so the residuals here among experimental units in this part of the field are going to be correlated with each other, and residuals in different parts of the field, maybe from this experimental unit and this experimental unit, are going to be unrelated to one another. So you can basically model that correlation matrix and incorporate that into your linear model. But we know from last time that a linear model here that just relies on ordinary least squares has basically looks at the residuals in this fashion. Okay, so what does this mean when I put this matrix up here like this?
Just calculating the error for each point and not taking into account, like it's just like you have that regression line, and it's calculating the error, like we're talking these squares, right? So it's just calculating the error, squared errors off of the line, and not taking into account the data points next to it, right?
I think, yeah, more or less. I don't usually think about it in that way, but basically, so this represents a covariance matrix among all your residuals. So say in the last example here, we have 12 experimental units. Okay? So we have 12 residuals. So you can imagine this covariance matrix here is being 12 by 12. Okay? And on the off diagonals here, they're going to be represented by the covariance between two residuals. So this may be the residual so maybe the residual between this experimental unit in row 4, column 1, and this experimental unit in row 3, column 1 is going to have a covariance here in this part of the matrix, right? And typically in ordinary least squares, we just assume that covariance to be 0. We assume that the residuals do not covary with one another. They're all independent. Okay, there's no covariance structure. And on the diagonal here of this matrix would represent the variance of those residuals. Okay, so in ordinary least squares, again, we assume that all the residuals are independent. So these covariances here on the off diagonal are 0, and the variances of those residuals are common. Okay, so the same variance, residuals all come from a common distribution with the same variance. All right. So that's what this represents here, and that's our baseline assumption, unless we tell the model to fit it otherwise. All right. So again, if we have a situation like this, we can model. We can model some sort of covariance structure among the residuals to capture this information in terms of plots resembling each other more, and residuals resembling each other more that exist in the same parts of the field. So a typical model for spatially correlated errors or residuals in field trials, I took a lot of this just directly from that the book I sent you. Is it ISRIC book? ISRIC et al. 2017. I took a lot of this directly from that book because they have a nice section in this in Chapter 7. And I'm too busy to retype matrices and equations into PowerPoint slides. So it's just, why reinvent the wheel twice, right? It's just. All right, so we have a typical model for spatially correlated errors for field trials is the first order autoregressive model, okay? Or we can do it in 2 dimensions. 2 dimensions, you can also do this in 1 dimension. Basically what this means is we're going to model a correlation among the plots, okay, in different dimensions. So plots that are closer to each other are going to correlate with each other compared to plots that are further apart.
I have one question. The slide, 2 slides up, like that row, is that individual plots of genotypes, or are those like blots, like in a row or column?
These are just individual experimental units in the field. So you could think about this as, it doesn't really matter what the treatments are, okay? They're just experimental units that are laid out spatially like this. Okay. All right, so again, this models the residuals as correlated based on the distance between plots in the row and the column directions, okay? And with the correlation decreasing as increasing powers of the correlation with distance. And I'll write this out for you. I'll have it written out in the slides. So once we set this up in autoregressive model, so this autoregressive model means that basically the correlations are going to regress towards 0 as the distance between the plots increases. Okay. You'll see it in the math here in a bit. So we can use this direct product to efficiently write out the complex variance covariance matrix residuals. Don't worry about that for now. Don't worry about that for now.
So we need to feed into the model the field structure.
Mm-hmm.
We could feed into this the structure of the field.
That's right.
So we can't do it with the NAM data, we don't have the data for it.
Exactly, yeah. So you need to know in this situation like this, you need to know the row and column designations for every single plot.
Yeah, because I was trying to see if I can do this with the sets, but I don't know if I can do that in the NAM set. There's 4 sets, but we don't know the spatial layout for the sets.
Right. That's right. You need to know the spatial layout for something like this. Yeah. Good point. So if you lose that information, you can't do this. All right, so I copied this right out of the book. This is more or less what I want to say. So and then also in order to do this, we need to have the data sorted correctly. Okay, so we want to sort the residuals, or basically our observations. If we sort the observations in our data set, we sort them by rows and columns. And if we do that, I guess the point I want to get across here is how we basically calculate this covariance matrix. Okay. So this variance covariance matrix here can be written as the direct product of 2 submatrices. All right. And these submatrices now are going to be, the covariance matrices, or the correlation matrix. In this case, the correlation matrix among the rows and among the columns. Okay. So if you have, in our example, we have 4 rows. Okay. This correlation matrix is going to be 4 by 4. And the correlation matrix is symmetrical, so only the elements on the lower half of the diagonal are shown. All right. So, and then each of these elements here is going to be a correlation between the experimental units in the different rows and columns. I guess for the different rows in this case. So this is, again, we have 4x4 field layout here. Or, I'm sorry, a 4x3, so we have 4 rows. So this matrix here, specified by sigma r, is the correlation matrix among the rows. This is going to be a 4x4 matrix in real life. And what this indicates here is you have one parameter here, a correlation parameter. This correlation parameter is the autocorrelation parameter in the row direction. Okay, this we don't know. This is estimated with the data. All right, so we don't set what this is. The data is used to estimate this. What you set in the model is the structure of this covariance matrix. Okay, so once this is estimated, then you can see that rows that are closer to each other, this would represent row 1 and row 2. Let's see here. That's better, right?
So you said in real life it'd be a 4x4 matrix, or is it 4x4 or?
There's no
Give us a tip.
pen.
The
Just
column.
Just an example.
would
Yeah.
be, what, 3 then?
This is, yeah, since in our example we have 3 columns. So this would be a 3x3 matrix. This is the correlation matrix among the columns. I was hoping I had a pen option here, but there's no pen option here in Dinesh's computer. Must have an old version of PowerPoint or something.
You need a pen? Oh, sorry, mouse.
No, I wanted to write on the slide directly. Anyway, so this would be basically, this would represent the correlation between row 1 in the column here and row 2. See, you can see since these rows are going to be close to each other, they have a strong correlation. As the distance between the rows increases, this would be the correlation between row 1 and, in our example, row 4. Since this correlation value here is less than 1, as you increase the power here, this number is going to decrease. Okay, so you have a decreasing correlation here specified by the exponent. So that's what the structure of the matrix looks like. So you're going to have decreasing correlations here as rows become further apart and as columns become further apart. All right, so I said up here, or I didn't say this in the book, it says this, but I would say exactly the same thing, that the way you have these submatrices here that indicate the correlations between the rows and the correlations between the columns. And the way we take this information then and put it and use it to derive a single big covariance matrix among all of our residuals is that we use direct products. Okay? And ASREML speaks the language of direct products. So when you specify the R covariance structure in your ASREML model, which I'll show you, you use basically direct product notation to build that covariance matrix. It makes things really easy in terms of specifying those covariance matrices, which in other software I find extremely confusing myself. But maybe I haven't spent enough time with it.
Aaron, maybe you covered this last time with us at direct product.
That's what I'm going to do right now.
Okay.
I mentioned it last time, but I didn't actually talk much about it. All right, so we're going to take the direct product between these two matrices to specify our covariance matrix. So direct product. So a direct product, otherwise is symbolized by this symbol here, a circle with an X. It's also known as a Kronecker product. Heard of a Kronecker product? You looking at Kronecker product on your phone?
When we have covariance.
Okay. So this indicates a direct product or the Kronecker product. And if you have two matrices here like this, A and B, the Kronecker product between these two things is going to look like this. And what I want you to see is, how should I do this? So you have basically, when you take the Kronecker product like this, you basically multiply every element in this matrix by this element. And then every element in this matrix by this element. every element in this matrix by that element, and every element in this matrix by that element. Okay, so you can see if you look at this matrix here, you can see up in the upper left-hand side here. And, you can see these elements up here are basically the product that I just described. So x times d, x times g, x times k, x times e, x times h, x times l.
That's a direct product.
That's a direct product, yeah.
And
Take
you get those
this
values.
whole matrix and multiply it by that, this whole matrix multiplied by that, this whole matrix multiplied by that and that, and you get this big matrix. So the dimensions of your new matrix are going to be, in this case, it's 6 by 6.
Do you call each of those a direct product, or is the whole table the direct product?
This operation is a direct product. This is the direct product of the Kronecker product of these two things right here.
So
This
multiple
is
things
the
that-
result.
So multiple things are called a direct product. So like each individual one is a direct product, and the whole thing is called a direct product, or is it just the matrices?
The matrix
of
is the direct product. The matrix is the direct product. Yeah. This is the specific matrix
So
operation.
Kronecker, is that how you said?
Yes, direct product and Kronecker product are synonymous.
Okay.
That Kronecker delta is not synonymous.
What's Kronecker delta?
I don't know. I'm pretty out of my depth right now. That's just something.
So yeah, this is an operation in matrix algebra. So if you want to, this is called a direct product. It's basically a way to build this type of matrix from these two matrices. And I'm not good enough at matrix algebra to know exactly when else this is useful, but I know it's useful for building these covariance matrices.
I'm frankly a little confused about what we do with a covariance matrix involving what we're about to talk about with the experimental or as it regards to plant breeding. Like when would we report a covariance matrix on flop, like spatial?
We're not going to report the covariance matrix directly. We're going to use that to get better estimates of our variety performance in this case.
So
The whole
it's
idea
just
is
another way to
it's
try
a-
to pull out variance.
That's right. So it's a way to account for spatial variation. Okay, so you have spatial variation in this field. You want to account for that and adjust for that,
We're just getting
especially when you have big blocks. Because when you have big blocks, big experiments, say 200 varieties or something like that, you're trying to compare them. In every block, you could have varieties that are in totally different parts of the field with an experiment that size. So, and there's spatial variation in the field, and we want to account for it. And this is one way you can account for that. You can use augmented experimental designs. You can use special incomplete block designs, things like that. This is just another way to account for that spatial variation.
You didn't have the layout of the field, but we knew a check was in each block. Can we use that as our for the that's our guide for this?
variance from check.
Is that what you said? Would that be effectively just using like this set block as it is? Probably. Probably the same thing.
I
as
think
just being block.
I think if you're going to leverage a check for accounting for spatial variation, I would just maybe fit a model for an augmented experimental design. You do that. And then I'm going to talk about, you can combine those types of approaches with these approaches for accounting for spatial variation using the residual covariance matrix. Okay. And the reason why, as I mentioned, and at the beginning of chapter 7 in that book I sent you, it gives kind of a brief description of the experimental designs you can use to account for spatial variation. A lot of those involve incomplete blocks, things like that you will fit as fixed effects in your model. Here we're talking about accounting for that variation by leveraging the covariances among the residuals, okay, which are random in your linear model. Right now we're just talking about regular linear models. The only term in our linear model is the only random term is the residual, and that's it. And we're going to leverage this covariance matrix among those random residuals to account for that spatial variation. And the reason why I'm going down this path is because we're going to use similar types of terminology, similar types of methods to talk about using BLUP and genetic covariances to leverage relationships among individuals to get predictions of genetic effects. So, I mean, we could spend, well, you're in experimental design right now, right? So we could spend an entire semester talking about all the experimental designs we could use to account for spatial variation. Where was I? Okay, here's the direct product stuff. So this is a direct product. Does that make sense to you guys? Okay. All right, so here's an example. Okay, again, we have a field laid out here, 3 rows, 4 columns in this case. This is an example from the book. I guess it's the transpose of the example I had at the beginning, but that's okay. So here then we have the correlation matrix here, the autoregressive correlation matrix among the rows. In this case, it's 3 by 3. Okay, and this is the autoregressive correlation matrix among the columns. It's 4 by 4. You can see that this correlation coefficient here, this is, of course, bound by 0 and 1. Or no, it's bound by -1 and 1, so it's less than 1. And as you increase the power of that, it's going to decrease in value. Okay? So as columns get further apart, the correlation is going to decrease. As rows get further apart, the correlation is going to decrease. And then to build our R matrix here, the covariance matrix among our residuals, we're going to take the Kronecker product of these two things and then multiply by the error variance, all right, to get that. So when you do estimate, what you need to estimate in this model then are just 3 parameters in this case. You have the autocorrelation among the columns you need to estimate in the model. Autocorrelation among the rows needs to be estimated, and then the residual variance needs to be estimated. So 3 parameters need to be estimated. You could think about this matrix as being unstructured. So what if I said this matrix was unstructured? What would I mean by that? So if you had specified an unstructured correlation matrix here among your columns, then each of these would be different. Okay, and you need to estimate each of these separately. You'd have to have a single estimate for every single element here on this side of the matrix. So in that case, then you'd have to estimate 1, 2, 3, 4, 5, 6, 7, 8, 9 correlation coefficients, which, unless you have tons of data, isn't really possible. So in this case, this is basically, this simplifies it, and it allows you to only estimate 2 here to describe the structure of these matrices.
For that error term, you said the residual error. What is that? Is that residual just like blocks and effects of rows and columns, or is it including like genotypes or?
Well, so you
have to draw out that like
Pooled with everything, right?
So you would have a on top of this, you'd have a linear model that accounts for the factors in your experimental design and your treatments. So put that in your linear model, and then the residual variance is going to be whatever you can in the linear.
Okay, great.
I'm not very familiar with autoregressive correlation, but am I correct in my understanding that you basically see what effect row 2 has on predicting row 3? It's kind of a simplified idea that that's why it's 1 when you're saying what effect does row 3 have on row 3? Well, it's all the effect.
More or less. I mean, they're related to each other. Yeah, the relationship between them.
Because I could only find it with temporal data.
With what data?
I could only find like a description of it using temporal data.
Oh.
Which I was having a hard time with.
Yeah. Well, I mean, it's the same idea though. We have things that occur more closely in time are going to be more strongly related to each other compared to things that are more
What
distant in time.
effect does observation X have on observation 1X and 2X?
Yeah, exactly. Okay, so you take that to build your R matrix, and once you do that, you get a matrix that looks like this. And again, this matrix is symmetrical, so you only need to show 1/2 of the matrix here. And so, you can look at all these different elements here, but you can see that up here, again, I wish I had a,
So this assumes that there's a constant equal relationship between the covariances for the greatest plots, which may not be true, right?
a constant covariance.
So like, we assume that in your top set of blocks, they all have an equal relationship to the surrounding blocks, and that's the same relationship as further down the field, that those all have the same relationship. But you could have a gradient where the field has a certain nutrient level, and then it suddenly
Yeah.
changes.
Yeah.
And so the gradient between these plots up here, where there's this quick change in gradient, is not
That's right.
the same as where there's a.
That's the trade-off. I mean, in this case, you only need to estimate one correlation coefficient. So it might not, in these models, it's a balance between simplicity and how well you're actually describing the data. So in this case, this is trying to balance those two things. But so it might not be the perfect.
And what you do to your data then, as a result?
It could, yeah. I mean, I think accounting for, even if the correlation is uneven across the field, I think accounting for some sort of correlation is probably better than not accounting for it at all.
Right.
So we'll talk about model fit and stuff like that. And we talked a little bit about that last time. Okay, so you can see that these elements up here, these would be, since this data now is sorted by row and column, row first, column second, all the elements up here would come from the same row. Okay, all right, I just want this one. All these elements up here would come from the same row. That'd be a better way to do this.
Once you make it, just copy it so you can paste it to yourself.
Yeah, that's a good idea. So these would all come from the same row right here. So you can see that this is just basically a function. The correlation between these experimental units is just a function of how far apart they are in terms of columns. But then as you go to set down here like this, these are now coming from different rows and different columns, and so the correlation between these experimental units is a function of both the correlation between the rows and the columns that they occur in, right? All right, so this is, if you actually put in some numbers here, if you actually put in some numbers, in this case we're putting in the numbers, I think what I read was they put in the numbers for the correlation among rows being 0.9 and the correlation between columns being 0.5 or vice versa. And here you can see then in this actual numerical example that as experimental units become more distant, their correlation decreases. Right? So this represents the residuals of the experimental units that are furthest apart in the field. Okay? So those have the lowest correlation compared to experimental units here that are very close to each other in the field. They're going to have a higher correlation, depending if they're in the same row or same column.
And that's because it isn't a perfectly square plot. It's like a rectangle, so the rectangle under it is technically closer. Like, is that why it's 0.9 versus 0.5?
Well, it would depend on the data. So it would depend on if the spatial trend is stronger in the row direction versus the column direction. You know what I mean? So,
would this normally be reported in such a way that you could backtrack and read it like, oh, row 1 with column 2 is exactly this? Or are you just meant to understand the basic format of this and be like, so this is the correlation between things that are close? Like is this just supposed to give you a general overview and idea of the correlation that was seen? Or be a blueprint of exactly where it came from in the field?
just an overview. Yeah.
Because like it doesn't have a legend.
This here, you mean?
Yeah.
And I mean, we're basically gonna model trends here.
Mhm.
And we're gonna model those trends and then account for spatial variation. Yeah, this is meant to be. I mean, you could roughly use this to diagnose sources of variation in your field. So if you estimated these correlation coefficients using your data, and you found that the correlation in the row direction is really strong, correlation in the column direction is really weak, you could say, okay, well, there must be something in the field here that's causing that correlation. It might be something interesting.
Input.
You could follow up on it, and then maybe use that to inform your experimental designs next year. I don't know. Okay. All right, so that's kind of the gist here. And I guess what I wanted to do is go over this script now. And again, I'm going to have you guys go through these scripts here and do some exercises with them later on, as soon as I can get you a license to ASReml. For now, we're just going to kind of go through the script, and you don't have. Does Candy have any licenses of ASReml in her lab?
I don't think so. She's not on school.
I thought we were talking to Emirates and having him run some of the scripts for me.
Emirates and Dinesh both have ASReml, so you can
Our
always.
postdoc have you met him?
I don't think so.
Yeah, he's like a pretty hardcore quantitative genetics guy in
Where'd he come from?
China.
Oh, okay. How long has he been here?
Since like towards the end of the summer. He's in that like the broom closet postdoc office, like right next door.
Oh yeah.
He's,
Oh, right there. Yeah.
Close,
You know,
yes. They're always crammed in there.
Yeah.
Oh my
All right. Let's see here.
So ASReml is just a license to use a package within R. It's like ASReml R.
It's the package. So ASReml is
There's
a
just
standalone software as well.
Okay.
So it originated as a standalone software. Basically just a software for fitting mixed linear models and estimating variance components. Implementing REML procedure for estimating variance components. That's why it's called ASReml. I forget what the AS stands for. But so since R became so popular, what they did is they took that standalone software and they used it to create a package for R. So now you can get the standalone ASReml, which actually is more advanced and has more bells and whistles. You can do more. It's actually more powerful. But you can use a fairly powerful version also just within the R environment using this ASReml package.
Do you think MSI has licenses?
I checked.
They don't have it? Yeah, I'm going to work towards getting a site license. I just need to rally some people.
So I checked it in there, so we made some changes.
So yeah, so that's what it is. So basically, to use this, you basically download the package, and to download the package, you have to have a license. And then once you download the package, it allows you to use these ASReml functions, which I really like. If someone can figure out how to fit models like ASReml and be as flexible and as intuitive as ASReml using free mixed models packages in R, I'd love to talk to him.
I'm sure
Spend a lot of time with them.
I'm sure ASReml will hate them for it, but.
Yeah, I mean, I think it's possible. It's just really hard to figure out. I probably have to spend some time with a statistician. Okay, so here I'm going to. Yeah, this is corn data. Can change my working directory. And I think I still need to load up the ASReml library. And I'm going to load in this data here called corn data. This is what my corn data, can you guys see this okay? Feel free to move to the front. This is what my corn data looks like. So this is corn data with, I think we have 4 replications here, lots of different hybrids here, okay, specified by their pedigree. And then here I have the data arranged in passes and ranges, which pass in my old terminology is equal to row. Basically a row range, and pass is like a column, and range is like a row. Okay. So you can think about this as column and row, pass range. 1 pass to the planter, and then 1 range in the field. and this is yield in terms of tons per hectare. So that's what it looks like. So you want me to change my rep as a factor. I'll do that right here. I need to set these things as factors. Make them all factors instead of integers. And then we can do that. So again, rep, 4 levels of rep, 205 different hybrids, corn hybrids, 18 different passes or columns, and 92 different ranges, or in other words, rows. Okay, so I mentioned before that in order to get ASReml to use the row and column information for making the spatial adjustments, we need to have the data ordered in the right way. Okay, so that when we calculate that covariance matrix, the covariance matrix can actually be related to the data. So what I'm doing here is I'm ordering the data. Okay, I'm just taking the data, I'm reordering it by pass and then range. All right, so that's what this does.
So it just knows when it makes a direct product, it has it like laid out correctly?
Yeah, exactly.
Okay, to,
Yeah.
to match what you actually did in the field?
Yep.
Is that something we should do in our data, or is it IC should have it over here?
I mean, my preference always is to leave the data as raw as possible in the actual file, and then make as many modifications to it as you can within the script, because you can easily go back and look at an annotated script and see exactly what you did to the data. You can't go back and figure out how exactly you sorted the data, which columns you deleted, and all that kind of stuff. So I know it's more convenient sometimes just to open up the spreadsheet and manipulate stuff like that, but you lose information when you do that kind of stuff. So it's just, you know, but I do it as well. I just need to do this really fast. I just need to delete these columns and reorder it, and then instead of figure out all the lines you need to.
Save it as a new spreadsheet with a different name.
You could, but then if you really wanted to remember what you did with the data, you'd have to create some sort of README file or something like that to say, okay, on this date I created this file and I resorted it and deleted these columns and removed these observations. If you really wanted to track what happened to your data.
I did exactly that like
Yeah.
a month ago, and I hate myself for it. It's I can't track back what I did.
When I imported, I put what I did to it in as a note in the markup file.
You mean the
Like if I go and I need to change something in Excel before I import it, I save it as a different name. And then when I import it into my README, that's when I put a note that says same as
Yeah.
except I.
Okay. Yep. I mean, however you track that kind of stuff is your own business. But I'm just saying it's important to track it. And just doing stuff in scripts allows you to automatically track it. Okay, so we have the data now sorted, and this data here, now the first model we're going to fit is basically just, we're going to analyze this. We're going to analyze this now just as if the rows and columns don't exist. We're just going to analyze it as a randomized complete block design. So when we analyze it as a randomized complete block design, we have the yield here. We're going to specify the basically the hybrid effect indicated by pedigree here, and a rep effect because things are blocked, right? And the data.
So you're doing that as a fixed effect then?
Yep, these are just fixed effects. We actually haven't specified anything in ASReml as a random effect yet.
Yeah, because if you had after the rep, you did another one, the random effects.
Yeah, these are just fixed effects.
Does it just by default assume it's a fixed effect?
Yeah, so in...
I actually don't know how, is that R or does ASRM always assume it's a fixed effect?
These are fixed effects.
Okay.
When we have them just like this, we tell ASReml to treat it as a fixed effect.
Okay.
If we want to treat it as a random effect, we have to add another line here. All right, so we get that, and we, it tells us that it converged, and everything looks good. And we can look at our ANOVA table here. Tells us we have differences between our hybrids and our reps.
So far, what's the strength of AS Dremel versus just LM or GLM?
Well, for this, nothing. So you would get exactly the same result here if you were to fit. So let's just fit that LM.
That's what I thought you'd say, actually. I just wondered.
You're just testing me, huh?
No, I wanted to be sure. If you were like, oh, this giant thing is the difference, how have you missed this so far in the lecture? I'd be like, oh,
No.
So at this point, it's really so easy.
So it would tell you the same. I mean, it's a little bit, well, I mean, rounded. So you see the sums of squares are the same between the GLM model and the ASRM model.
Here, the best approach is fixed.
Now, okay.
Good question.
Yes.
Yeah, so.
Just in like base R, if I build a linear model, does it assume my terms are fixed or random?
Fixed.
Okay, so it's always.
Which function are you using?
I guess it depends on the function then. What are
So I think it's. I'll talk a little bit about this next time. But I think it's important to specify or to recognize that there's a difference between a real mixed model when you really treat something as being random versus when you assume something to be random and you calculate your expected mean squares for testing hypotheses. So in SAS, you guys use SAS at all?
Just that's Purdue, yeah.
So in SAS, there's a procedure called procglm, which is really similar to just a GLM function in R. So in procglm isn't the mixed models procedure. It treats everything as fixed except for the residuals, but it has a random statement. You can tell procglm what you consider to be random. The only difference that makes is when you do that, is that when you tell something is random, it calculates your expected mean squares differently, and that informs you which mean square you should be using, or which source of variation you should be using to test for differences between treatments, for
You
example.
prints up the equations for it. It's great.
Right. But the underlying model underneath isn't really treating those as random effects. It's not modeling any sort of covariant structure or anything like that. It just tells you, okay, which are random, how do you calculate your expected mean squares, and which sources of variation should be using to test hypotheses, which informs you how your scope of inferences you can make. And that's it. So in the GLM function here in R, that doesn't have the capability of treating anything as really random. Everything in this function here is treated mathematically as a fixed effect. Okay. There's no. Yeah, that's pretty much it. There's no ability to model covariance matrices among these effects with a GLM type of function. So it's more nuanced than I think sometimes initially meets the eye. So those are all fixed, yeah. Okay, so all right, so this is where the difference comes in now. So this is not where it's going to be different between just a regular old GLM or LM model in R. So now we're not treating anything, we're not causing anything here to be random except for the residuals. But nevertheless, when we're going to try to model the covariance matrix here to get at the correlation structure between our residuals. And so this, in ASReml, this is what we can do to do that. So here we're telling it to specify this covariance matrix here, and we're specifying this covariance matrix here among the residuals according to this direct product between the pass correlation matrix and the range correlation matrix. Okay, this colon here indicates the direct product. And right here, pass, I don't have any, you see that I'm only modeling the spatial covariation here in one direction. We talked about two directions before. Here we're just going to do one direction.
You're just going to ask actually the AR1.
Right. So this is modeling that autoregressive correlation here
range
in the direction of range, but it's assuming that the passes are independent. Okay. So you're basically going to be taking this is not, sorry to the people in Monsanto, but this is basically telling that we're going to take the direct product. This is going to be for the passes. And this is going to be, let's do a 3x3 example here. Okay, and this is going to be for the ranges where we have these.
Squared and
Yeah, squares, yeah.
Yeah, you do squares here, right? Like that. Okay, so you're going to take the direct product between these two things. And so you have your, for the past situation here, you're just taking the zeros are all off. You guys know what I mean? Okay, so this is going to basically be a block diagonal matrix. When you take that direct product, so all these elements multiplied by 1, all these elements multiplied by 0, so you're going to end up with this block diagonal thing that looks something like this. With block diagonals, so it indicates that observations within the same pass have a covariance structure, but then the observations have, in different passes have a covariance structure of 0. Yeah, so that's what that's doing.
This probably help with our efficiency flows and stuff. Not
Yeah, we
not
should-
this structure, but doing this pass and range.
Good, yeah. There's a lot we can explore with that. We need to do that someday. Okay, so that's what this does. So that's what, now this is where we're going to be using the benefit of ASREML here. So we'll run that, and if I can get it to run. And it converged. So that's good. And I always lose my cursor here. For some reason, whenever I run something in R, the cursor goes back to the screen. Okay, so that's in one direction. This is in two directions here now. So now I've just added that AR1 function to the path. So now we're doing what I talked about before. We're doing it in two directions, right? So we'll run that. That converged, so that's good. And so here now is, we're going to look at the model comparisons here. So we're going to look at the AIC. We talked about this last time.
I think I understand what the log likelihood converged means.
I don't think it's really that important to worry about the details of this, but basically,
You want it to do that.
It's
Basically-
trying to best
basically-
fit for the data.
that's right. So basically what the software is doing is it's doing a search for the right estimates of the variance components. So it's searching all over the place for these variance components, right? And then it fits the model with a certain sample variance component, and then it calculates a log likelihood. And then it fits it again by adjusting it a little bit, calculates another log likelihood. And then as the variance components converge on the correct or the best estimates of variance components, the log likelihood isn't going to change anymore. So it's searching for the best ones, and the closer it gets to the best ones, the lower the log likelihood is going, or the higher the log likelihood is going to be. And then once it detects that it's no longer making any improvements, it says it converged. It says it got to the best points, and this is as good as it's going to get. I'm not going to make any improvements if I...
This reminds me of the iterative way that the computer runs generalized linear models. It just keeps cycling until it finds the best.
Sure.
Yeah, similar thing. Yeah. How exactly, I'm not sure what exact method ASREML uses in terms of the algorithm to get the maximum likelihood estimates of these variance components. There's several different types of algorithms.
But that line basically just means we found it.
It converged on something, yeah. If so, I wonder what would happen if we do this. I talked about those unstructured correlation matrices. If we fit an unstructured correlation matrix, you have to estimate a different correlation coefficient for every cell in that matrix, which means you have to estimate a ton of parameters, right? And so when you have a situation like this where you have a ton of parameters to estimate and not very much data, it's very unlikely you'll get it to converge. You'll just keep going around forever. You know, say, okay, there's just too many things to fit here. There's not enough data to fit it, and nothing's converging, right? So if we change this, I think it's this UN. I wonder what happened.
Blue screen, income.
Error.
Is it on S? Does it have it?
I'm expecting when he finally gets it to just see like a fine smoke to come out of the computer.
Did we not drop these back in the time?
No, I printed these off earlier. I just forgot to grab them.
Man, you were fast.
I should have
I know
said.
you know you run the weekend.
I should have. I should have said yes. My running is really falling off a cliff, actually. Between 4 kids and a busy semester, I'm out of shape.
I'm sure you're right around now.
See,
You're trying
let's
to catch the kids, right?
I don't know what exactly happened here, but basically, I fit these now as unstructured, and I just did what I talked about in terms of
Just
estimating tons of
also maybe
parameters.
Oh,
And I don't know.
it ran out of its memory allocation.
Yeah.
Like it literally has a stop so that you don't end up just freezing your computer because it uses all your memory.
Right. There's too many things to estimate there.
This is like the unstructured.
Yeah, the unstructured.
Okay.
What I was hoping it would do is, what I thought it might do is it might just run for a long time, and then it would say, okay, never converged.
I think it would if you somehow
I don't know if it
gave it a
would.
better workspace.
I don't think we have enough data to do an unstructured.
Put it on MSI and see if they can play.
Yeah, so do you have any server space we could borrow?
There's nothing here really more complicated I can fit. Okay. Well, you get the point, right? All right. So we're gonna fit these. Oh no, I messed this up. This is for the autoregressive correlation matrix structure. And then we're going to look at the let me go back up here and run this again. Okay, so these are the AIC model fit criteria here. And you can see that actually the one, smaller the better, and the one where we fit a correlation matrix in 2 directions here, both for the pass and the range, has the best fit to the data according to that criteria.
Just to reiterate, the other ones you only accounted for like the range covariance, and the other one you only accounted for the pass covariance, and then you accounted
For the first one, we didn't account for anything.
Okay.
Just ran as a randomized complete block design.
Okay.
For the second here, we accounted for the range. And the second one here, we accounted for the pass.
If there wasn't any effect of a pass, you would basically make it as a 0, so you get the same result if you account for both.
Let's there's no, if there's nothing for the past, then that would be the one you want to fit here.
Well, what I'm saying is, when the model realizes, gee, there's no effective pass, so mathematically, it won't have an effect for it, and thus, your matrix, the results will not have any factors on the diagonal, or...
Well, I think your question kind of gets down to model selection, so which model, you're suggesting that maybe the software should know automatically?
No, I was saying, just pick one that adjusts for both, and then if there's no effect of one, it won't matter, it'll still get the best result.
Oh, that would be a smarter software. Yeah, yeah. I mean, I think what you need to do is you need to examine your data first and try different types of models, figure out which one fits the best, and then fit that one and get your estimates for that one. The software will only tell you exactly what to do. If you fit this here, if you fit a correlation matrix here among the passes, it's going to adjust for them. You're saying that, well, it should automatically know that if it's not better, then it shouldn't.
What I'm saying, I guess what I'm trying to say is, if pass has no effect and the range has no effect, when we model it, the pass terms would be 0 for the correlation to each other, because they won't have an effect.
They won't be exactly
Because
0.
Not exactly 0.
They'd be non-significant.
Maybe not significant, but they're going to be slightly different than 0. So you're going to get some adjustment. You might get some adjustment. You might get some adjustment regardless of whether or not it fits the
But
best
you
fit
still
to
want
the
to pull
model.
out that variance because you're still trying, like this whole exercise.
I mean, if there's significant variance to pull out, then yeah, you want to pull it out. But if there's really no variance to pull out, if there's no covariance in the past direction in your data, then you run the risk of, because these parameters here you're estimating, there's air around these things.
Mhm.
So if you're fitting things that have air on them, you run the risk of adding more noise to your data if there's no real trend. If there's not a real trend, you don't want to mess with it, because the more parameters you add to your model, the more likely you have slight errors because of error and parameter estimates. And then also the more things you add to your model, the more likely you are to overfit your data. You don't want to overfit your data. This is what these model selection criteria here help you do, is they help you basically balance between variance explained and overfitting. You can explain all the variance in your data if you fit a million things in there, but then you have an overfit model that's not useful for making inferences outside your data set.
And if I remember from yesterday, the numbers at the end are how many variance components are in that model. And that's why with the
Yeah.
randomized complete block, you have your pooled error, so it's one error argument, basically. And then with the SB2, you have 2 covariance and your pooled error. And does that you showed at the beginning of this lecture an equation, and it was on your slides, where you had your 2 covariance plus your error. Like, it was all together. And I forget the context, I'm sorry, I can't be more specific. But it was one where you went both ways, you had 3 arguments, and then here I see you have 3 covariance.
On one of the slides, you said?
Yeah, that equation. No, right at the bottom there. So R equals error times the sigma error, and then the
Field.
but you had 3 arguments in that one, and that was your 2 directions.
Yeah, that says your directional. And then back to here.
And there in your 2 directional, you have 3 components, and then again, 2, 3 variance components in the equation.
1, 2, 3. I'm trying to remember now. I don't remember the equation for.
Well, I have it notes from
Yeah, I see.
the last one. Variance components per model is what that last number is in those check fit equations.
Yeah, it's related to that, but I'm not sure if this is a function of that or if it's just literally that. There's an equation for it someplace. I can try to find it. I don't remember if because this would be 1 for the error variance, but then 2 because I guess we're estimating. Yeah, no, that's right. Yeah, that's right. Because here we're estimating the one correlation coefficient plus the error variance.
Yeah.
Here the two correlations plus the error variance.
Yeah.
Yeah.
Basic stuff.
Yep.
Like
Got it.
beginning of ANOVA, good, how to use it in these models. So getting
So if you fit the unstructured one,
exactly.
you can see that this will go way up because you're estimating
Like, I want to know.
Oh, yeah.
unique one for each of
This
these.
is like a really good, like,
Yeah.
So then it penalizes you.
It's like how you start.
Be like in
and
the-
where you want to end up. That's not too bad.
16 range. Yeah. 17. What papers
Okay, so here, as I mentioned last time, ASReml has this, well, this is actually a general function in R, but ASReml makes use of this predict function to get basically the adjusted means for the hybrids.
What is your bluff number?
So then we can do that. We can look at those, and so ASReml spits out these. These are basically adjusted means. So what these are, and this nice thing that ASReml does this is that it takes the intercept in your model and adds it to the blues of each hybrid effect. So you get something that's on the same scale as your original data. You know, when you guys look at blues, right? They're negative values and positive values. And this adds it back on automatically. And it gives you a standard error with each of them, and it tells you whether or not it was estimable.
And this is just the estimated, like, in this case, yield, I guess?
Yeah, yield
Okay.
for each hybrid.
So, I'm confused about the difference between, like, a mixed model and a blue. Like, is it a type of mixed
So
model, or like?
you can get blues or blups from a mixed model.
Okay.
We'll talk about that in a bit here, but real briefly, a blue is best linear unbiased estimate. It's
Right.
going to be an estimate of a fixed effect.
Okay.
Okay, from a mixed model. Or it could be from a non-mixed model as well. It can be from just a general linear model.
Okay.
It's just an estimate of a fixed effect. A blup is a prediction of a random effect. So a blup you're only going to get from either a mixed model or an all random model. It's a prediction of a random effect.
This almost reminds me of like a far more accurate confidence interval. Far more accurate.
What?
You've got error around the predicted mean. Just
Yeah.
like not mathematically, just like conceptually.
So this is going to these standard errors are mostly going to be, I don't know if this data is unbalanced. These standard errors are mostly going to relate to how many observations were in the data set. So for the ones that have a higher standard error, you probably only observed this a couple different times in the data set, whereas these ones that have lower standard errors, they have been replicated an additional time if you have some unbalance.
Makes sense.
Yeah.
You're adding the y-intercept to what values we use to get these values?
The wider.
You're adding the y-intercept to what values to get these?
The model intercept to the blue. Yeah. I mean, ASReml does this internally, but if you just got the blues from
So
a
blues
base
have-
function in R, you'd have to do it yourself.
Blues output the number and how much greater or lesser it is than the y-intercept of the model. Okay. I see what you're saying.
So bluffs are predictions of random effects, and as far as I can tell, the reason why we call random effects predicted and fixed effects estimated is mostly because of convention. But it kind of gets down to the fact that if a random effects are assumed to be sampled randomly from some distribution. And I think when you're estimating effects or random effects, you're thinking about things in terms of predicting future occurrences of that same random effect if it were sampled from a distribution. Whereas fixed effects are treated as something that's sort of fixed, something you can repeat in an experiment year after year or experiment after experiment. And it's something you're interested in. So you want to estimate those fixed effects, and it's something that you can observe again if you want to. Whereas a random effect, by definition, you can't observe again because it's randomly sampled from some distribution. So It's kind of, I wouldn't lose any sleep over that, but that's the convention. All right. So we're looking at the predictions here. And then I was going to, there's not really much else I was going to do here besides so if you fit the two here, so these are the spatial blues. These are basically the blues we estimated with the spatial model. Can't remember, I think it's maybe the spatial 2 model in 2 directions. And these are the blues just with analyzed as a randomized complete block design without accounting for spatial effect. So you can see, you know, they're related to each other as we'd expect they would be, but there are slight differences here. They're not perfectly related to each other. So depending on whether or not you account for the covariances among your residuals, you're going to get slightly different estimates of your hybrid performance.
Those are really related to each other. Like that's
So you
like
wouldn't,
R equals 0.95 right there.
yeah.
But sometimes a little bit of difference, you know.
Yeah, I mean, this might not be it might not be the best data set. I should keep searching around for data sets to see what the relationship is weaker.
Eventually, the more noise in your field design, the less we help with
Yeah, that's right. So not a profound difference here, but you can imagine a situation where there could be a pretty big difference. You know, and you know, maybe at the top here, if you're making some selections in your truncation point is in here someplace, you might choose a different hybrid or two based on which model you fit.
If you have unbalanced, say if a plot gets lost, that might affect this as well.
Yeah, I mean that if you have unbalanced data, you definitely need to use blues. You know, just take averages. I guess we're pretty much out of time here. I wanted to briefly talk about. Well, we can cover it next time. Okay, so that's a demonstration of how you can use covariances among residuals to account for spatial effects. And we're doing this to account for as much variation as we can and get the best estimates of our hybrid performance that we can get. And we're doing that leveraging the covariance matrix of the R matrix. And then next time we'll talk about mixed models, and eventually we'll feed into leveraging covariances among random genetic effects using pedigree data, sharing information between relatives. It's basically you just add another random term to the model. Right now, the only random term in the model is the residuals, just like it's just a regular general linear model.
This all seems really complicated, and in my head I was just kind of thinking like, why would you go through all this? This is a lot of resources, but it occurred to me in reality, if you're just doing year after year of yield trials, like you'd have all of this built into one long like sequence that you could run and
Yeah.
automate the whole process, and just every year, as long as you have the same inputs,
That's right.
it's actually
In
Like it's
over. Oh, this isn't a big difference, but let's imagine the difference is a little bit bigger over a long period of time. If accounting for your spatial variation a little bit better allows you to make a little more accurate selections over a long period of time, it can make a big difference.
But this is definitely a product of the computer age.
Yeah, you can never fit these things. I mean, mixed models in theory were developed back in the 1940s and 1950s, right? But they were never really even used at all until the 1970s in animal breeding and the 1990s in plant breeding, because you just you didn't have the computational resources to do it. These mixed models involve inverting large matrices, which takes a tremendous amount of computational power, I guess, compared to the old days. Not these days, but
It shows, I've just shown Ben this paper, there's this graph of showing like citations for mixed models. This red one shot up. I know in 2005 there's been citations for mixed models like really took off in GBIE.
Oh, really?
Type literature, yeah.
where's the paper?
It's from that graph. It's like you reached, I can send it
It was the exact year. that
Crop science had like a
Char
UID
and GL.
issue in like September, October or something.
Oh, it's in that one?
That one.
Yeah, I should look at that.
Yeah, it's like a.
Yeah, that's the case. I mean, the guys who worked in mixed models a long time ago, they would spend all their time converting matrices by hand. That's what they would do. Just to show, some basic properties of a mixed model, they spend months converting a relatively small matrix.
Is that by hand inverting it, or they're doing that?
I mean, they probably would use
Cars,
machine
right?
calculators or something like that, but. So, that's where we're going next time, and hopefully by next time, I can get you guys some software. See if they emailed me.
It's just little bitty things that might help improve the efficiency. We've done all these big gains, now I feel like we're fighting for these small additional gains and things, Or gains in efficiency, I guess you can say.
Yeah, it's a very different mentality from potato.
Well, they probably use this in potato too. This?
Is it F1?
Well, it doesn't matter what type of progenies. It doesn't matter what type of progeny you're looking at. If you have a big block and you have spatial variation in your block.
Yeah, but like, for instance, in the reds that I'm working with, they don't even yield as secondary to just like how red is it. And that's not like you can do a quantitative measure of like spectrum analysis, but they literally just use a color wheel like this is a 5 for redness. So it's a little bit.
So why don't they have colored bars, take pictures of all the potatoes and then have it use a colored?
I'm not saying no, this stuff's possible. I just mean like culturally within like I haven't talked to one.
It's not a bad idea. It's like, it sounds like an easy drone type thing. Or, I guess you have to harvest potatoes, drone. They're not working drone. It needs to be above ground.
A drone that digs, you get a mole, not a drone, a mole.
I'll tell you what kind of like tech invention would be heavily utilized in potatoes is the minute we
should
are
get
able
lots
to
of
like X-ray root structures without a back, like just like drive something over a field and see roots in 3D. Potatoes and like tons of computational heavy stuff will just take off. Well, that's
I mean, you and all other species want to see the root structures, it's.
well, potato roots are holding them back. They only absorb like 70% of the available nutrients because they're like these stubby little root systems in the more cultivated varieties.
So there's a lot of selection on the potato, but not as much selection on the root structure.
Oh yeah, because like there just wasn't enough money
So-
to engage in that large scale like
So-
so
Sometimes confused on, like, some of this is like nomenclature and different names for different things, but like, AS Rummel versus mixed models versus blues and blobs, like, which ones are which, and like, I'm just confused on like the hierarchy of which one's which, because like I know I've covered all of it, it's been all very spread out in the past, and I'm just confused on what's what, if you have time.
Yeah. So you have a mixed model.
I know what each of them are used for loosely, but.
Type of model. Mixed, maybe a mixed, typically we use mixed linear models. You get into other scientific areas that use lots of non-linear models, but aren't really use a lot of mixed linear models. Okay. Type of model that includes both random and fixed effects. Yeah, that's it. So mixed models then look like this. In matrix form. Yeah, so these are going to be your fixed effects. These are your random effects. Yeah, and here, plus.
Okay, so in Rex's class, when we were solving for bluffs, we were doing all this work just to fill in the matrix to go into the mixed model to make a prediction. Okay,
And these are going to be the vector of the random effects.
right. So that whole bluff equation is just to solve for that vector. To get values,
Yeah, I
then
mean,
plug into that vector.
the bluff equations basically are, I mean, the mixed models equations are basically a compact form to show the solution for estimating both the fixed effects and the random effects simultaneously.
Okay.
So Henderson derived the equations to estimate in the same model both fixed effects and the random effects. So you see those compact matrix equations? That's what those are, the mixed model, mixed linear models equations. Which shows you the solution for these. But those are just equations. So you can have all the components of those equations. But inside those equations, there are still variance components, variance parameters you need to estimate. You can estimate those variance parameters with the data using software like ASRemel.
Okay.
ASRemel, Rock, mixed. There's
So that's the stuff that like kind of crunches the numbers on the covariance between different things within these effects. Even when you're calculating the Bayesian and bluffs.
that's right.
Okay. This diagram is helpful.
So we have these are basically software. Software to use Remel to estimate variances.
Okay.
So it's between ASRemel and say LU4 or LU.
Just the syntax and probably some underlying details of how, what exact methods are used to implement Remel. Remel's, basically this is restricted maximum likelihood, maximum likelihood is a basic approach for estimating parameters. In this case, parameters are estimated variances. How exactly you implement this, the details, are possible detail differences. How you do that. So there could be differences in that. What forms, what equations they use, something like that.
Okay. So like with like a G by E type study, you want to model like the yield taking into account like the rep and the location and all that. So use like the mixed model in total, but we use bluffs for like genomic selection because we can estimate just the effect of the genotype on the trait value for like genomic selection. That's why we talk about like if you're gonna.
The only reason we talk about bluffs when we talk about genomic selection is because we are treating either the genotypes themselves for random effects, or maybe the markers as random effects.
Okay.
So by convention, we call
That's like our.
the estimates of those random effects by convention are called predictions.
Okay. Okay. And so bluffs are kind of what more lend themselves to like estimated reading values, sort of, because we get like the total like. Maybe not entirely, but like this gives us a better idea of like how good our line is just genetically, and then the mixed model as a whole is how we would model how it perform in a field based off of like other location effects and.
I mean, in a mixed linear model, you apply it to a field data set, you probably have fixed effects that are accounting for rotations and
Yeah.
reps and stuff like that. And then if you wanted bluffs on the genotypes, you might specify them as random effects. Because it gives you a couple different advantages. One advantage is it would allow you to share information between relatives. So since here we have these bluffs are going to be assumed to have some sort of covariance matrix here. So since they're random, they're assumed to come from a multivariate normal distribution. And this multivariate normal distribution is going to have a variance covariance matrix that, for genetic purposes, if you're interested in genetic effects, could be specified by a relationship matrix here indicated by A.
Right.
So this allows for screening purposes, allows sharing of information between relatives. Through interests.
So Aaron, above that, you put random effects estimates, would that be predictions then? Since you said that.
Yeah, I mean,
So estimates of random effects are called predictions, or?
I mean, I'm just trying to
Yeah, I understand.
show the similarity. These are basically the similarities.
Okay.
You want to estimate the values in each of these vectors, and the estimates in these vectors are by convention called blues. The estimates in these vectors are called bluffs. You can argue to the blue in the face about whether it's supposed to be an estimate or a prediction.
Instead of fun.
And I'd ask people like some of the people that work with. There's a guy in Nebraska named Dale Van Vleck, and he's actually a professor at Cornell, and he studied under Henderson, who derived the Mr. model equations. And he's really, not quite sure why you differentiate between predictions and estimates. But I think there's probably a good reason that it's.
I'm gonna take a photo of this one. Yeah, because it's like I've learned all these things like somewhat in separate classes, and then I'm sitting in experimental design trying to like, how does this relate to what we've talked about in Max's class? And neither one of them are breeders, so they don't know exactly, like, I don't know what I'm asking, they don't either, so.
You guys covering mixed models and experimental?
Yeah, we're going to really briefly.
What software are you going to use?
Like just, I don't know. I think they're just gonna let us know that they exist. Like a lot of our homework and stuff is like, here's this field data, like just like doing ANOVA, but make sure it's designed correctly, and like, drawing up the variance components and doing the right F tests and making sure we understand that stuff. But it's like they cover a lot of designs and show us how to do it, but we don't necessarily do all of it. Like part of it's just like, you probably will need to know about this, so here's some notes on it.
It's too bad that you don't have so in SAS, it gives you all those F tests, it shows all what's being used to test, and I don't know if that's an R, it's too bad, it's some sort of package that helps you do that sort of.
But it's helpful to know. It's helpful to know like how to do it. Like yesterday, I started to click a little bit. Like if I draw an ANOVA table, I'd be more confident in being able to write out the estimated mean squares like by hand. So it's good to know a little bit. Yeah, we're covering like, generalized linear models and stuff like that. 'Cause that's pretty easy to can get through your head. But we have to do like these project proposals. And part of my project is a G by H, so I know these models. So I asked Nancy about it, and she said, "Hey, Aaron's teaching her. Go talk to him." So that's
Okay.
yeah.
I'm not going to get in. I mean, there are a bazillion ways that you can model GID with this model.
Right.
Passion that very much.
Yeah, I'm just curious about it as a whole, because I know these are used so much in genetics, and that's part of the class I'm interested in. They're only gonna like kind of mention it. And
Jeff Neihart is going to talk a little bit about GID later on.
okay. Thank you.
Yeah. Come back anytime you want.
Yeah, I have. When does the class actually end?
11:30.
11:30. Okay. Maybe we'll show for we have live meetings at 11 on Tuesday, so I can show up for the first chunk.
Okay. Yeah, that's right.
Yeah, Tuesdays, yeah.
Today's Thursday.
Yeah.
Yeah, time flies.
Time flies. Yeah.
All right, so I'll have to run this on Amer's computer, but obviously yield is on our result. I put something up here, environment maybe, and set design check. So we've got our sets, and then our check line is within the sets, the Iowa 3023. Do you think I should put environmental set here, or do you think it should go in the first? Because this is effectively like a block.
I think it should go in fixed. So what I would say is that unless you're trying to recover some sort of shared information between sets, maybe sets the modelers random.
I guess I'm thinking back to my old stats days, so blocks are random, and that's not put into random on some other sets, ASRM guides?
But in your old stat stage, were you actually using a mixed model?
No. That's just a, is this repeatable? No, our block's not repeatable.
Right. I would sure use the fixed effect. You just want to adjust for that effect.
And then you suggest that do family as an effect. So we've got family, and I've got family, the string nested within family.
Yeah, so I was wondering as if effect and then string
I've got to come to this column second.
Yes, what I wanted to know. This is where I have to do some research here. Is we need to. 'Cause here, I think this is just going to give you one estimate of family variance.
I can parse each family out.
You could try that first, yeah.
So I would just subset it. And then
You could do that first, but if you wanted to do a single model, what you should try to do is try to fit families that have heterogeneous variances. And then it'll, just like that example I went over in class, it'll spit out a variance for each, a residual variance for each location. I'm sure you can set it up if we put our heads together here, so that we have a separate genetic variance estimate for each family in the same model. Basically a heterogeneous genetic variances model across the different families.
Was that the wheat example or the corn?
The wheat example, we looked at specifying heterogeneous residual variances among locations. But that, I'm sure that we can find a way to fit the heterogeneous genetic variance model across families. I don't know off the top of my head how to code that, but I'm thinking it can be done.
Okay. I'll look into that.
I wonder if the solutions would be much different than just subsetting the data. I don't know.
I can start with subsetting it.
Yeah, start there. That's the simpler one. And then I just got word from, we're almost to getting that software ASRM set up on the server.
I'll just bug Dinesh or Emrit to let me run my code.
Okay, that's good for now. But
It's not preferred, but you know.
one thing that's
we
kind
can chat over lunch, and I can.
one thing I'm kind of annoyed about is that I thought that if we installed the ASREML on a server, we could just call the software from our desktop computers, but it turns out that that capability is still under development, and the way it works right now is that you have to actually log on to a virtual machine. So you'll log on to a computer on the server, and then you'll run ASREML on that computer. So it won't be actually running on your PC.
Well, that be more powerful then.
Could be, yeah. It'll probably be
So
more.
make sure that we load the data onto the.
Yeah, that's what I mean. It's kind of annoying to have.
And we can't. We have to be here.
No, you could log
I
in.
guess I
VPN.
can log in through the.
Yeah.
I could what is VPN in?
Yeah, VPN in. Yeah, and once you VPN into campus, it's just like you're on campus. Yeah.
All right, I don't want to interrupt your lunchtime.
But then after, it sounds like they have the capability of implementing a way so we can call software from our PCs, and so once they get that developed, we can use that.
Yes.
That'd be more convenient instead of having to log into a virtual machine.
There's one person at a time.
Yeah. But nobody else is really going to be using this besides you at this point. Because Amherst and Dinesh have their own, and I have dreams about analyzing more data, but it never quite comes to fruition. So.
You know what? You've got tons of things on your plate, so.
It's tough to get analyzing things.
Yeah, I'm not making professors handle all of the stuff on your plate.
Good people like you around this.
No. But I'm asking you a question about how to do things. I mean, and I'm only I say passion what you do. I mean, you've got analyzing field trial stuff and taking lines and reviewing papers and writing grants, and you got a family to take care of and class to teach and grading.
It somehow all works out.
I
don't
guess.
know. It's things just we get time to do stuff. You somehow figure it out.
I guess.
You'll figure it out someday.
Letting it done, well.